Welcome to the Guide to R for Santa Clara University Economics students. This is tutorial number 5, multiple regression. In this tutorial we're going to learn how to run multiple regressions and put the results into a table and a few other things that are useful for regressions, including how to conduct f-tests for joint hypotheses. As usual, you can find the scripts and the data if you want to need to download anything at this website. Okay, let's get started. We've got our tutorial number 5 here, and this is called t5_multreg.r. And as usual, you should set the working directory to your specific folder. I'm going to just run the whole section down through the data here so we can get started on the regression part. And once again, we're using the California School District data. What we're going to do here is replicate the regression table for table 7.1 of the Stock and Watson textbook. And there are 5 regressions in that. We've already talked about how to run the regressions. When we run multiple regression, it's the same as how we ran a simple regression. Namely, we give the regression a name. For example, in this case, reg2 equals LM for the linear model. And then we have the dependent variable, which is the test score in the district, the little squiggle or tilde sign, and then after that, all the regressors that we're going to use separated by plus signs. So this is kind of intuitive because we're thinking of this as a linear combination. Beta 0 is the intercept plus beta 1 times STR plus beta 2 times EL underscore PCT, etc. So we just add additional regressors for multiple regression with a plus sign, then a comma, and then where the data are coming from. Once we run all those regressions, let's just go ahead and do that. We'll highlight Reg 1 through Reg 5, hit the Run button, and you'll notice they've all popped up here in the upper right in the values, under values, right? So those are all the regression results. Let's display them in a table, and I'm going to skip down to this second Stargazer command here, which is one that includes labels for the columns. So notice what I've got here, Stargazer, then parentheses, then all of the regression results that I want in the table, separated by commas, in the order that I want them, then a comma, then the SE list. And remember, the objective of this SE business is to use the heteroscedasticity corrected standard errors. And it needs to be set up like this, and make sure that the regressions are all included and they're all in the same order that you put them into the table in the first place, in this case, numerical order. Now, a new thing also in this Stargazer command is the column labels. It's helpful when you have more than one regression in a table to give them some kind of reasonable, sensible titles for each regression. So I've put these column labels in, and you'll see how they come out in just a second. So let's run this, highlighting the whole command all the way to the last parenthesis, hit run, and I've got the regression table right here. And looking at this, you'll notice a few things. Each regression is represented by a column. The multiple regressions, of course, are defined by having more than one regressor. So in column 2 there, for example, we have added the student-teacher ratio as one of the regressors, the English language percentage as another one. By now you should know that the asterisks are telling you the p-value for the following hypothesis test, that the value of that coefficient in the population is exactly equal to 0. When we have 3 asterisks, as we do, for example, in the case of this coefficient, it's telling us that we can reject that null hypothesis, that the slope coefficient is 0, at the 0.01 level. So the p-value is less than 0.01 for that hypothesis. And we'll work through the implications of all these regressions, but you can see that we have a nice, neat table that summarizes a whole lot of information from 5 different regressions in this, including the R-squared, adjusted R-squared, etc. So it's as simple as that. That's how we can run the regressions. And let me return back to my script here. I want to talk about a couple of other things that we can do in R when we've gotten some regression results. One function in R that's extremely useful is called predict. After all, one thing that a regression is good for is for prediction. You've estimated the relationship between one variable and perhaps several regressors. And for example, in regression 3, if I can kind of sneak back down here, there's regression 3. We had the test score in the district being predicted by the first 3 regressors there in the table: the student-teacher ratio, the English language percentage, and the meal percentage, the subsidized meal percentage. Now, once we get those regression estimates, we might ask the question, suppose we had a district that had a certain set of characteristics. And I'm going to just create a new fictitious school district that has the following data set. And this line here, the new data, creates a new little tiny data set for one hypothetical school district that has a student-teacher ratio of 20. 20% of the students are English language learners, and 50% of the students are on subsidized meals. And we can just set that up. Then we use the predict function to predict what would be the test score for such a district based on the regression results. And the predict function is very easy. We give it the name of the regression that we're going to use, the model for this prediction, then a comma, and then the data set that we want to predict for. So if I highlight these two things, I've given it the data and the regression to use. If we look down in the console here, this number here, 650.385, is the predicted value of the test score for that hypothetical district. And this can be a kind of useful way to think about what are the implications of your regression. And you can see also the predict can put confidence intervals around those predictions, and we'll talk about that in class. That's straightforward to do. Now, the next set of code here in this tutorial talks about how to calculate standardized coefficients. Standardized coefficients are a way of rescaling the coefficients so that they are in terms of the standard deviations in the data for each of the variables. And I'm going to let you do those yourself in light of what you learned in class, and we'll talk more about that. I want to move quickly here to talk about a really important tool that we have for looking at our regression results, and that is how to run f-tests. And in R, we have a nice function in one of the packages called LHT, and LHT allows us to run linear hypothesis tests, including f-tests. So let's take a look at this and see how it's set up. Here's the standard setup for the LHT test. We start with LHT, that's the command name. Then in parentheses, we have the name of the regression, reg5. Then a comma. And then this is the hypothesis. Now remember, for joint hypothesis tests, we think about a set of restrictions on the parameters or the coefficients. In this case, we're going to test the joint hypothesis that the coefficient on the meal percentage variable is equal to 0 and the coefficient on the CalWORKS percentage, remember that's a kind of a welfare support program, that coefficient is also equal to 0. So this is a joint hypothesis, and it's set up inside that C framework there. Then we have a comma. Then we have something here that says white adjust equals HC1. And this is a heteroscedasticity correction. You just need to include that there whenever you run one of these LHT tests. So let me highlight that command and hit the run button. And now let's look down in the console and we get those f-test results. So it says linear hypothesis test. It reminds us what the hypothesis is. And you should think of this in terms of the coefficients, that those two coefficients, the meal percentage and CalWORKS betas, are both equal to 0. This is telling us what is the restricted model and the unrestricted model. It basically is going to remind you what the regression was that you used here. That was regression number 5. And then it gives you some information here. And the F statistic for that test, which we will talk about in class, is that number right there under F. 290.27, and it gives you the asterisks, which will tell you something about the p-value and therefore the statistical significance. And you'll notice that 3 asterisks means a p-value somewhere between 0 and 0.001, as is interpreted in this table. So that's suggesting that we can reject this joint null hypothesis at a significance level of 0.001. So what we're saying is it's extremely unlikely that we would have gotten the regression results we did in this sample if it were the case that both of these coefficients were equal to 0. It's a very small p-value, and therefore we strongly, at conventional levels, reject that joint null hypothesis.